Started. Last week I talked about complexity. This week we're going to talk about a completely different topic that we've been playing with. Okay, we've intersected the two every once in a while, but what I'm going to talk about today is really about function. And when I talk about function, I'm not talking about mathematical functions. I'm talking about mechanical functions. All right. So, not knowing exactly who all has been in here and has taken different classes, I'm just going to start first with a little bit of what a function is. Okay? And so I should have said this work has been a focus of several students before, and we have a couple students now that are working on this. Ashwin Raj is a student that's working on some of the stuff at the tail end. He's working on writing his thesis right now, so hopefully he is in seclusion in a monastic state. But Amaninder is also working a little bit on this in terms of the pruning and trying to find the value of different representations. So, all that said, what is a function? Okay, so we have a lot of different definitions. A function is an action that a system does, or it's a relationship of the intended input to the desired output, or it can encompass many different tasks. I mean, there's a lot of these different definitions that have been bantered around. We have different views of function. So in artificial intelligence, we might say how a device works, or what a device is for, or what a device does for a user. You know, from design, we might look at it more from the point of view of moving from the problem to solution, transformations, internal, external, generative, use for synthesis. So there's all kinds of stuff out here. Okay? I'm going to play with a little bit more narrow definition of what a function is. We're going to take the point of view of more of a transformation. Okay? But from that, what are these three products? Do you recognize them? Okay, so do they share the same function? What is this guy? Well, we'll start here. What is this? It's a hairdryer. Okay, what's its function? To dry hair. What's this? It's a clothes dryer. What's its function? Dry clothes. What's this guy? Heat gun. What's its function? Heat things. Okay, so at one level, you know, everything is kind of named in English after what it does. Okay, it goes so far as when you introduce yourself for the first time and you're trying to get to know someone, what's one of the very first things that you're going to talk about? How do you describe yourself? Almost always it's by what you do. Okay? And so in English, in our American culture, functionality is the designation of what is something. Okay? All of these do different things, but can they be used for the same thing? Right? Can we use a hair dryer to dry clothes? How many of you have done that? Okay? Can you use a heat gun to dry paint? Okay. Can you use a hairdryer to dry paint? How many of you have done that? How many of you have used a clothes dryer to dry paint? All right. Remember back when you were doing Father's Day stupid sweatshirts and you got the puffy paint and you drew a little star in a rainbow and say, "I love you, Dad," and you had to dry that puffy paint? Well, you toss it in the clothes dryer. So they can all do similar things, but they're not the same. So we differentiate them not just based on the functionality, but based on the performance of the functionality. So some of them heat air a lot faster. Some of them blow air a lot faster. Some of them allow for more control of the heating and more control of the blowing. Okay, so there's a little bit of a balance there. So when we talk about these functions, we need to understand what kind of function model we're going to be dealing with. Okay, so we can describe models as normative or descriptive, right? What is a descriptive model? Am I using terms that you guys know? So a descriptive model is a model that is going to be from typically a controlled vocabulary, and it is a description of. Okay? Normative is kind of an intuition, is going to be kind of describing what it could be. Okay? Formal versus undefined, these are some different dimensions, and if we start looking at an example of a hairdryer, this is a function model drawn from the literature. Okay? But if you look at it, it describes kind of what's going on. There's no formal language, no formal vocabulary involved. It's just kind of very normative, very bleh, okay? Can you build a program to reason on this kind of function modeling? Not if it's undefined vocabulary in a normative format, right? So that kind of lies over there. We have the function structure for a hairdryer again. This one coming out of the functional basis or the design repository from Oregon State, okay? And here we have a little bit more structure imposed, okay? But the vocabulary used within each of these boxes, each of them being a transformation activity, there's some rules and some not followed rules, okay? So in this case, it's more describing the existence, what's going on, but it's kind of defined, kind of not defined. It's kind of in the middle here. We can break all kinds of vocabulary rules when we do it, and I'll show you that in a little bit. We have another functional model for a hydraulic pump. And this is more of just a function tree, and that lies over here. And then we have the AFNOR. This is a horned beast coming out of France. In this case, what they're describing, that bluish circle is your device. And your device, your hand interacts with plate 1 and plate 2 through the device. Okay, this is a vise, by the way. And the glue interacts with the plates through your device and your hands, your eyes, and different things. Okay? And so again, but this is very normative. This is describing what could be. Okay? It's not describing what is. Then we have, overlaid on top of everything it kind of hides. But this is an example of a FBS. Okay, so it's a lot more detailed, a lot more controlled, and it's also describing what is. Okay? And so we can see that we can plot a lot of these different types of function models all over this space. Okay? If we want to support something that is generative design, okay, forward design, we need to be able to support some normative stuff. Okay? But if we want to do any computational reasoning, if we want to have a program available to us to say, hey, this is possible, this is not possible, we need to be over here in the formal. Okay? So what we want is a model that's up in the normative and in the formal. Is there anything up there yet? All right, so that's what we're trying to figure out. What and how can we start to move stuff up and over there? Okay? And in order to get there, we're starting with what we think is the best first place to start, and that's on trying to define a formal vocabulary. Because once we get the formal vocabulary, then we can move up and down on the normative and descriptive. Okay? It's easier to move that way, rather than taking something that's normative but unstructured. Okay? And so to do that, we're starting with this basic black box or block diagram approach. Okay? How many of you have seen function models that are based on this before? All right, this is what we teach in the undergrad. This is what we teach in the graduate classes. This is very straightforward. I didn't even touch on all the other function modeling approaches in the undergrad, and only every once in a while will I touch it in the grad. So we have inputs here, we have outputs, and there's some sort of transformation that's happening. Okay? And typically, historically, we deal with mass, energy, and signal. Mass and energy, we can apply basic laws of thermodynamics, conservation principles. Signal, you can't do that. Moreover, signal is actually always going to be carried via the energy or the mass. Okay? So there's a slight nuance that we propose later on. But for simplicity, I'm going to present all three of these like this. And we can take a high-level description of what we want our thing to do and convert that into this state. It's almost a state diagram. We're going from a person at point A, and we want the same person at point B. And so we're going to transport that person. So we have mass that's flowing. Okay, we have conservation of mass. We want the same person in and the same person out. Okay. A lot of times we talk about function models being solution neutral. I disagree with that. Okay? Function models are form neutral, not solution neutral. Okay? Because every time that you lay out an architecture, a series of functions, that is a solution. You can rearrange it and do the functions in a different order, and that gives you a different solution. Okay? Some best practice, analyze the product through the eyes of the user. You're always trying to ask the question, is this doing what I think it's doing? How do I know it's doing what I think it's doing? And then keep the system boundary as large as possible. In none of these am I actually drawing the system boundary, which is ironic because that is almost always the most difficult thing. And I'm not presenting any of the work that we've done on the system boundary issues, but that's been the biggest thorn for us. We'll walk through a little bit, and then I'll get into some of the new stuff that we've actually done. So this is an example. We have a product, a motor. Right? What's a function of a motor? Convert electrical to mechanical energy. Now, are there other things that convert electrical to mechanical energy? We have solenoids. Okay. Are they converting it to the same kind of mechanical energy? Linear versus rotational. Okay, so there's some differences here. And depending upon how abstract we want to live with respect to the description of the flows, we can jump from solution to solution. Okay? Make sense? But is this the only thing that's happening with the motor? I mean, do you guys think that we're only bringing in electrical and we're only kicking out mechanical? Well, okay, so that's a little bit of a challenge. We need to recognize that we have the desired function versus maybe the actual behavior. So in the actual behavior, we have electrical coming in, mechanical coming out, and oh, by the way, it's getting hot, so we have thermal energy coming out. All right, and we have something called the what law of what? To help us guarantee this? Okay, what does second law of thermodynamics tell us?
You can't convert all of your input energy out.
You're going to have some loss somewhere, right? And so once we know that we're doing something with energy, we know we're going to have a loss in the system. Once we know we have a loss in the system, we don't know how much, but we can start doing some qualitative physics reasoning on this, okay? And we can start saying, is there something I can use this thermal energy for somewhere else in my system that could be a positive, it could be an input, okay? But we have to make sure that we understand that we have the desired versus the behavior, but once your behavior, and you capitalize on the behavior, then this becomes your desired. So it's a little bit tricky. You can't put a clear barrier between function and behavior. Okay? The basic process we normally operate with, we find an overall function, then we're going to start identify all the interfacing objects. How will we know it's being used? Convey what's going on using action verbs, recognizing energy and material must be conserved. And then we blow this up and we start breaking it down piece by piece. Oftentimes, as we break it down, those pieces become subsystems. So we have to figure out a way to heat up air. We have to find another way to move air. Okay? And those become subsystems that we can design many times independently. So the function decomposition becomes really your first approach at organizational decomposition of your design project. Okay? All right. So that's a very quick, normally it takes me an hour and a half to go through that in 4010. But let's look at the research topics, the issues. So we have some gaps. So number one, we want simulation models. Okay? Well, we're using function descriptions to model something that doesn't yet exist. Okay? And when you're modeling something that doesn't yet exist, you have to somehow try to capture all of the environment in which it's going to, in the future, exist, which becomes a big challenge. How much fidelity in that model, in that simulation, do you need to use? Okay, we want some, but we don't need necessarily everything. Okay, we want to be able to ask questions about these models, right? The only reason that you guys create any model of any kind is to be able to reason on it. Right? You don't create a finite element model just for a pretty picture. You create it to learn something. You create it to interrogate it. If you're going to create a CFD model, it is so that you can learn something. Same thing with the function models. You create these to learn something. Okay? What are those something? Those are the reasoning questions. Simulation models, we would also want to be able to use this for our virtual world testing. So we have to be able to have true physics in here somewhere. Okay? The modeling reasoning gap, we need a method that is flexible so that we can model something that doesn't yet exist. All right? A lot of disciplines, such as electrical engineering, have a great, very fast conceptual modeling tools like SPICE and stuff like that, where they can deal with black box models for resistors and capacitors and voltage. It's nice, it's well defined. They only have a vocabulary of half a dozen things. And then you can do all kinds of simulations that you want on it. For us, can you tell me in mechanical engineering what the finite vocabulary for describing everything that we need to describe? Gears? Well, I can make a lot of things without gears. Belt drives? Oh, well, I can make a lot of things without belt drives. Structures, kinematic mechanisms. Well, mechanisms, that's great. What about compliant mechanisms? Now I don't have joints. And so there's all kinds of crazy stuff. And we need a tool that can handle all that crazy stuff. So it's very flexible, modeling what does not yet exist. At the same time, we need a tool that can provide fast checks on reality. All right? So I want to be able to model something that doesn't yet exist, yet check to make sure that it is existable. Does that make sense? So that's that normative and formal modeling dimension that we were talking about. So we have some options. We could go with free language where the user defines everything and just use your own words to describe what you want. No real automated reasoning. You could do some pattern matching, but now you need a huge database to operate with the pattern matching. We could do a fixed or controlled language, but that's extremely limited. So we could do a lot of automated reasoning, but it's really difficult because we have to know everything a priori. Okay, that's a challenge. So what we're going with is a mixed language where we provide some atomic elements that we can use for basic reasoning, but those atomic elements can be built up into more complex, more intuitive language. Okay, so that's going to provide us both. And so let's look at some of the deeper requirements associated with function. Okay, so in the course of this talk, I'm trying to build up the case for a brand new language, a language of function. Okay, so we have some basic requirements. Many of these are coming from the AI field. Okay, so how many of you have taken an AI class before? Okay, well, coverage and consistency, validity are three very basic things. Okay, we also have physics-based concreteness, which is slightly different than validity, and then we have normative and descriptive modeling. We want to be able to support both, and we want qualitative modeling. So we don't want to just be able to do some physics, but we want to do some qualitative physics. You guys know what qualitative physics is? So I take a lever, right, and I have a midpoint, right? If I put mass here, I know it's going to lift, right? If I move the fulcrum over, I don't have to know how much I'm moving it over. I just know that this is less than this is going to give me less mechanical advantage, right? I move it over here, so this is longer than this. I have more mechanical advantage. That's qualitative physics. Okay? I don't need to have the parameters defined, and I want to be able to do that with function modeling. Okay? So when we talk about coverage, the representation should support modeling and reasoning with principles and devices commonly used. All right? What this is saying is, whatever language that we develop, whatever representation approach that we develop, it should be able to describe things like a camera, like the tripod of the camera, like a stapler, like a car. All right? Is it able to describe all of these? If it's not able to describe them, then we're missing on the coverage. Okay? So we are narrowing it down to electrical, mechanical, and thermal energy. And what we want to do is we want to support mechanical engineers. We're not talking about developing a function modeling language for industrial designers. Okay? I don't care about the aesthetics. I care about the functionality. Right? So that means that we're focused on the physics, the transport phenomena are really what we're of interest. In terms of consistency, so I said that we're going to take this basic notional scheme of a transformation model. Okay? This, by the way, is a hairdryer. Okay? And it looks pretty good, right? Except there are lots of examples of how this model breaks. All right? Specifically, in their own model for the database that they developed at Oregon State using their own vocabulary, they broke the rules. There is no such thing as hot air in their vocabulary. Okay? There is such a thing as gas. Okay? But they don't have any parameters or adjectives or modifiers to the gas. Okay? So that's a violation. They have conservation violation. We have electrical energy that's not being conserved. Where does that energy exit? I mean, the only place that might exit, possibly, it can't even come out this way. There is no exit for this energy. Therefore, this model does not conserve energy. Okay? We have violation by the definition, converting human energy to signal. Well, now you have energy in and signal out. And that is a violation of their own definition for that, We have human energy, human material, human signal. What is it that you're really importing? Definition, violation, conservation violation. We have all of these violations in this very simple model, in a model of something that we should be able to understand because it already exists, and by the people that created the vocabulary, they're breaking their own vocabulary. All right, we got an issue here. So we need to control this a little bit more. Okay? We want to look at validity against physics domains. Okay? So we want to be able to place whatever we're designing, this function model, into a virtual real world. And we need to be able to do some sort of simulation on it to see how it behaves. Okay? So we want to do an external validity against the world. The world of interest that we're focused on is really physical. It's mesoscale and it's governed by physics. All right? So we're not talking about chemical reactions necessarily. All right? We're not talking about atomic particle physics, okay? Mesoscale. We're not talking about global dynamic systems. Okay? We're talking about mechanical devices. All right? Now, and this is just going through and explaining, more formally exactly what we mean by each of the validity against laws of physics. This last bullet, for our validity, we also still want our models to be good enough. Okay, what does that mean? What does it mean to have a model that's good enough?
Accuracy.
What level of accuracy? Does it do what you want it to do? That's what we're talking about. We're talking about satisficing. We're talking about, can I ask a question and get an answer? Okay? And what is the confidence that I have in that answer? Sometimes it may have to be extremely accurate. Sometimes it doesn't have to be terribly accurate. It could be a very low fidelity model. All right? A very low fidelity model that all of you have made would be a free body diagram. Right? And you don't have to make sure that the angle on your force is exactly 90 degrees when you sketch that out. You're just trying to get an idea of where the load paths are. As you evolve that model into something in Abacus or ANSYS for a finite element, then it becomes more important. You're expecting it to give you greater confidence in your answers. Okay? So we're looking for good enough. That means that we have to figure out, in terms of reasoning, what is good enough. In terms of the concreteness, okay, we need to be able to capture all of the things that actually influence these function models. Okay, so the entities, relations, attributes, and grammar of the representation must be defined in terms of physical actions. Okay? So we need to start first with the physics and build our grammar and our vocabulary from there. Okay? So we have branch definition. We have a definition that was coming from the functional basis. And it says, the function to branch, to isolate a flow, be that material, energy, or signal, into distinct components. The separated components are distinct from the flow before separation, as well as being distinct from each other. All right? Does that definition make sense to you? All right, so I have something coming in, and I have two somethings coming out. Each of those somethings are different from each other, and each of those somethings are different from the original. Okay? Well, we actually have separate lid from can. So we're going to do work on material. Is separating if we have a can opener and we're taking the lid off the can. Okay, we're separating the material, right? So before we have the can closed, after we have the can and the lid. All right? So there's a separate, but we have energy coming in and energy going out. So we're doing work on this. We have to be able to capture that. So that branch definition is not just about branching. It's also about some work or energy being transformed or used. Okay? We have a vacuum cleaner where we could have air and dust that's flowing in with kinetic energy, and then we have air with less kinetic energy and dust with zero kinetic energy. All right, so these are kind of some examples, and they don't necessarily look the same. Okay, so this is how we can start to say, all right, if we start with the definition, can we grow into something that still has some physical concreteness? Okay? And we can look at normative versus descriptive, like I started off with. Looking at the different modeling approaches, we do have the function behavior structure model from Jarrow that argues that it's both normative and descriptive. Well, that's great, except for the fact that no one has used the SBF diagram or FBS diagramming for forward design. They only use it to describe design processes. Okay, so even though they self-argue that there's normative, it's not. Okay, so we need to deal with something, and we're kind of dealing with recognizing that the functional basis can be descriptive and the functional basis can be normative, and so this is maybe where we're going to play. Okay? And then we have qualitative versus quantitative. So we have a qualitative model of pump and motor assembly where we have water in, electrical energy in, we have mechanical energy coming out. Right? Number one, what's the problem with this? Okay, so we still have to have water coming out. Okay, so automatically we recognize that this isn't quite there. But from a behavior point of view and from the conservation principles, but we're capturing what we care about. Okay, the electrical energy, we're trying to get mechanical energy coming out, okay, with the water being moved to a different location. Okay, and so the quantitative model, we might be able to attach efficiencies, we might be able to attach some sort of power consumption. Okay, and so we need to be able to operate in both the non-parameterized and the parameterized worlds of these models. All right, so that's kind of all these different requirements. So let's look at two different things. First, we're going to look at the representation that we're proposing, and second, we'll look at the reasoning that can be done with this representation. So anytime that you're dealing with models, you have two different things, representation and reasoning. Okay? So our motivation, we talked about it, we want to enable reasoning in early design. We want analysis of functions, model checking on the physics, great. We have to build this formal representation. And so we start with this, and let's go ahead and refine that. But if it's a starting point, we can look at the vocabulary. So there are a lot of different vocabulary-based modeling approaches. A lot of people have really focused their efforts on trying to figure out what is the right words, verbs, for all these functions. Okay, we had helicopter functions. Jack Collins back in the 70s started it all. He said, and he actually did it from reverse engineering. He wanted to identify all the different failure modes that were happening in the helicopters. Okay, and so he had to have a way to describe what the things in the helicopters were supposed to be doing, and why they were no longer doing them was the failure mode. Then we had Kirschman and George Fidel offered up 4 functions. So Jack Collins offered up 30 to 40 functions, and George Fidel says there are only 4. And then we go on, the NIST vocabulary then evolved into the functional basis where we have 54 verbs. Okay? And each of these verbs has a definition. Each of the verbs is about a conversion input to output for the flows. And they spent all of their time focused on the verbs and very little time thinking about the nouns. Right? keep that in mind. We'll come back to that point. All of the work on function modeling has been focused on the transformations, on the verbs. Very little of the work has been focused on understanding the nouns, the things that are flowing. Okay? And the modeling, the vocabulary was developed based on a lot of reverse engineering. So they took apart a lot of things, tried to figure out how to describe all those things, looked at how they described all those things, and found the intersection of the words that they're using to describe those things, and said, well, that intersection must be our vocabulary. Okay? They've attempted different efforts such as similarity, design synthesis, failure modeling. In all of these, the similarity is just pattern matching. The design synthesis, again, is just pattern matching. It's like graph grammars. If I have this, then give me this and this. If I have this, then give me this and this and this. Okay? And then they have failure modeling, where they're flowing through the system and saying, if I break this here, what no longer flows through? Okay, so it's a causality analysis, and that's great, except it only is a forward flow causality analysis. It's not a backward propagation causality analysis, and it also doesn't explore what happens with where the other stuff would go. So it may not flow down the system, but it may branch and short out something somewhere else. Okay, and so this is the function set with the verbs at the primary and secondary. The way we get 54 verbs is there's also a tertiary level. And then we have the flow set, primary, secondary, material, signal, energy, and then there's also a tertiary set here too. Okay? For the most part, material, signal, energy, that seems to cover most everything. But then they have some weird mixtures. So we have human energy and human material. And a little bit later on, for the status and control, you can actually have human signal. And what exactly is all of this? Okay? And so we have some vocabulary level inconsistency with this functional basis that was proposed. So in terms of energy, is it really human energy? It's a mechanical energy that's being done. Okay? The biological, well, what's the difference between biological energy and human energy then? Wouldn't human be a subclass of biological? And what biological are we talking about? Is it chemical? Is it thermal? Or is it mechanical? Those are really the only ways that the biological energy can be expressed. Solar versus optical, hydraulic, pneumatic. So there's all these intersections. So human, biological, solar, we have source classification issues. Really what they're doing is they're describing where that energy came from. It's coming from the sun. Well, great. What is it? It's photonic. Okay? Or is it thermal? I don't know. It's both sourced as solar. Hydraulic versus pneumatic. It's really about the carrier. It's about air that's carrying that energy, or it's about fluid carrying that energy. That's how you differentiate between them. Is that really a difference with respect to the energy itself? No. And so we have some issues there. We also have definition level issues. So we have a verb to inhibit. We have another verb to extract and another verb to contain. Okay? So these are all functions as defined. Notional definition, so this is what they wrote their definition as. To significantly restrain a flow through a portion of the flow, though a portion of the flow continues to be transferred. To keep a flow within limits. To draw or forcibly pull out a flow. That sounds to me very similar. Okay, all of them are about a flow is about being constrained or forcibly moved. Okay, so what is significant and what is a portion? What is pull out? Where's your force coming from? How much force are you going to use? Limits of what? What what are you talking about? Okay, so in their definition, it's not a complete set. Okay, it's not a complete definition. And the reason it's not a complete definition is because they're operating within the English language. They're not creating their definitions from the base atomic entities. Okay? And so they're already setting themselves up for failure by trying to define words by using other words that are not well defined. Okay? We have model level inconsistency issues. Okay? I think I showed, yep, I already showed you these. But at the end of the day, we want to build a formal representation so we can do this computational stuff. In order to do that, we have to have all of this inconsistency issues sorted out. We don't want to let someone build something that is inconsistent. Okay? So model analysis against conservation and irreversibility, these are basic laws, universal laws. So we need to be able to handle that. So this is a very simple, high-level model of our ER diagram, or entity relation diagram. This is how we would define the things, material energy signal, versus our nodes. Okay? In our nodes, we can have environment, and then our elements. Is a geometric anchor point given? So this is our start. Okay? These are the things that are flowing, and this is our function. Whereas everyone else, if you just look at the relative ratio here between how much effort we went to describing function versus how much effort we went to describing the thing, it's complete inversion of what everyone else has done. Everyone else has spent all of their time trying to expand out and develop taxonomies and classifications for those nodes or the functions. Okay? But there's a reason that we can get away with this. What do you think the reason we can get away with this? And not worry about all of the function definitions. Do I apply the laws of physics to the transformations? Or do I apply the laws of physics to the things? It's conservation of material. It's conservation of energy. It's not conservation of a branching action. Okay? So physics deals with this. It doesn't deal with this. This is just a result of how we connect these things up. Okay? A couple things that we've had, that we can add. So we have our verbs, and we can append them with some attributes, such as efficiency. So your conversion of electrical to mechanical for your motor has an efficiency attached to it. Right? That's valuable information if you know specifically which system you're going to be using, which instantiation of that motor you're going to use. The energy, we can say, is it a residual energy or is it power? Okay, is it being used? Is it what's left over? And that can help us flip from function to behavior. Okay? And so beyond verbs, beyond the stuff that flows, the material energy or even signal, we have these attributes. Okay? And that's great. That's a basic representation. But we want to be able to do stuff with it. And that's what the reasoning is all about. So when we talk about reasoning, we have topological reasoning, we have topological connectedness, and topological conservation. Okay? So first, early state reasoning support. We're just making sure that stuff is fully connected. Okay? If I have something coming in, I need to have something going out. We can identify where the values might be missing. Okay? Where there might be a missing flow. We can do basic transport phenomena reasoning. Great. We can do checks to see if stuff is fully connected. We can check to see how one flow is derived into other flows. So now we can back propagate and say that this energy flow is coming from this guy, which means that this original source energy can be traced forward and backward. Now that causality analysis for failure analysis isn't just forward causality, it's also backward causality. Okay? And that's a powerful distinction that was not available before. Okay? So we have basic topological reasoning, we have a redundant function. Okay? So we have model state, redundant function F1. Yeah, it's just there. It's not doing anything. It's not connected to anything. Do you want it branch, but nothing coming in and nothing going out? Right, this is basic, elemental. You might put this in when you're starting as you're building a model, but at the end, your final model, you don't want this. And so you can run these checks periodically. We can have a dangling tail. Okay? So where is this coming from? Is it coming from another function? Is it coming from the environment? Where? We don't know. So it's not defined. So that's dangling. That's an error. We have dangling head. Where's it going? Is it going into the environment? Is it going into another? And so these are topological conditions that we can check periodically to see if our model is complete. Okay? Not necessarily correct, just complete. Okay? And then we can do a different kind of reasoning. We can check to see if we have orphan flows. So we have a flow into a function, but it doesn't come out of the function. Okay? And so that's an orphan. We have a barren flow, something coming out, but nothing going in. All right, I'm not sure if orphan and barren is a right, but we had to come up with something, right? We have one in, many out. Okay, so if we have one in, many out, we need to be able to trace which is going to which. So in this case, mass 1 leads to mass or material 2 and material 3. And so that summation needs to be held. Then we have energy 1 coming and splitting into energy 2 and energy 3. We could have a different situation where we have energy 1A, energy 1B both coming in, where 1A directly is E2 and 1B is directly E3. And so we can impose that level of control. Okay? We have many in, many out. And so these are all different things that we can reason on to see what's going on if we define it or if we don't define it. This level, you're probably getting glassy-eyed right now. Okay? And as well you should. Okay? So this is at the atomic level. Engineers will not operate at this level. Okay? We'll build our own vocabularies on top of it. Just like we use the basic Roman alphabet for English, German, French. Okay? All three of them are completely different languages, but we use the same letters. All right? We could talk about it, American English versus British English versus Indian English. They all basically use the same words, but the constructs are slightly different. Okay? So we're talking about the letter level here, not worrying yet about the words or the sentences. Okay? We have conservation reasoning, many in, many out. We need to make sure that we have the same volume coming in and out. Many in, user-defined derivation, energy transformations, material transformations. So these are all very basic elemental that we can then use to build other stuff. Okay? So we do not want to create, first question, why do we not even create these models? All right, how many of you have worked in industry? Okay. And working in industry, have you ever once created a function model? All right, so, but that's what's taught pervasively throughout the US, throughout Germany, and throughout the UK. Okay? Kind of in France too. Those are the only ones I know for a fact. So we teach it, but we don't necessarily use it. Why is that? Huh?
It's time consuming.
Perhaps it's time consuming. Okay? Is that because there's not enough value? So that cost benefit. So if it's time consuming, I'm putting in all this time, I better get a whole bunch of value out of it, right? The only way I'm going to get value out of it is if I have some sort of computational reasoning to support it. But now I become overly constrained by creating these models that take me a long time. So we're constantly in this vicious cycle. Okay, so we need to keep that in mind. We don't use these models in this way. This is a common complaint. Okay? We use the function models to describe reverse engineered products. We don't find very many instances where people created forward or generative design solutions using function models. So is that because we don't, we can't, or we just haven't been taught, or we haven't learned enough about it? We do not model in this way. Do we know how we think functionally? Okay? And this is a big question. In terms of functional thinking, how is it that we create these models, and can that tell us how we think about things? Okay? We use function models to generate solutions. Why not use them for feasibility? Why not use them for understanding the problem? Why not use them actually as a transition between problem and solution? Okay? And so these are some big challenges, questions that we're asking and we're trying to answer. And to answer one of those questions, we're going to delve into this idea of protocol studies and trying to understand how people think through watching how they do stuff. Okay, does that make sense? All right, so first let's ask a question. How do we create the models? Are we going forward? Are we going backwards? Or are we nucleating? So this is an example of forward propagation. I create my function chain, okay? And I'm moving forward in the temporal sequence, okay? Is that how we create function models? I don't know. We also have backward propagation, where I'm going from my desired output and inverting it and going backwards. Okay, that backward propagation. Is that how we do things? Or we have nucleation. I start with a few functions I know have to be done. Now, how do I start connecting them up? If I know how people create models, does that start to tell me how they think? Actions speak louder than words, right? You guys have heard that. What does that actually mean? You understand someone at their core by what they do, not what they say. So watching what someone does is more valuable than listening to them tell you what's going on. Right? This is a subtle but important tweak that we're playing here. Okay? We believe that if we can study and watch how people do things, finding patterns in that will help us figure out how they think while they're doing those things. That way we don't have to ask them what you're thinking about. Okay? It's a very important. We don't want to intrude on the process by asking them to explain. And so we've done an experiment. This was a hobby of Chiradeep several years ago that has now been replicated and is being written up as a thesis right now. Originally, we just did 2 participants, 10 years of experience, 2 years of experience. We had some sort of basic pre-selection survey to see what kind of experience they had with function modeling, design in general, and stuff like that. And we gave them a problem. Okay? Designing the problem was very important for the experiment. We wanted to have a problem that presented something new that did not exist, that none of the participants had any experience with, but that was familiar enough that they could envision how it would need to be done, but open-ended enough that there was not a single solution. Okay? So we have all these wonderful constraints. And in this case, what we said, hey, design me an automated clothes folder for a hotel. So you go into a hotel, you leave your bag of clothes outside, they go and wash it, that's great, but it needs to be on-site, clothes folding, large volume, unknown. You don't want to do a lot of sorting, so there's going to be some sorting that has to be automated and stuff like that. And you can even constrain it by thinking about what kinds of energy sources do you have available in a hotel. You probably have steam, probably have water, you have air. Do you have pneumatic? Probably not. But you do have electricity. All right, so you can play with that, and that now kind of constrains the system. And so when we're playing with this, we videotape people creating these models. Okay? And while we videotaped them, then we decoded it and looked at what blocks they put when, what kinds of arrows did they use, what kinds of connections did they use, and stuff like that. And some basic observations, flow names immediately followed the flows. So as they drew an arrow, they immediately wrote on top of that arrow what that arrow was. So if it's arrow, material, arrow, air, arrow, water. Okay, does that make sense? So immediately while they were modeling this. However, we looked at and we saw a function name follows the function only 4 out of 13 times. So when they drew a box for the function, they did some other stuff and then came back and filled in the word for the function. All right, what does that tell you? If I'm drawing something and I'm labeling the arrows, but I'm not labeling the boxes until later, which is more important to you in your thinking? Is it the function or is it the flow? Probably the flows. Is that it's taking precedence. I need to define that quick. The functions, if I'm waiting until later, it could be that I'm waiting until I get all the inputs and outputs and then figure out what verb describes what's happening here. In which case I may not even need to have the flow or the verb, the flow, the function. Okay? And we've done other experiments that actually showed in terms of interpreting, you need the flows, but you do not need the functions. Okay, so this actually aligns with some other work, and we're thinking more in terms of the flows. Then we can start looking at the model growth and seeing how often do the two different designers use a forward versus backward versus nucleation. And we see that there are almost equal forward and nucleation for functions, but when we're doing forward and backward, it's really about the flows. We also see that the experienced designer nucleates. The novice designer goes forward. So the novice designer is starting with what he has available and moving forward step by step by step, whereas the experienced guy is looking ahead saying, I need to be able to do this and this and this. Now, how do I connect stuff to make that happen? Okay, so if you're developing a representation or you're developing a reasoning tool, you need to be able to support both of these. Both a tool for experts, allowing nucleation, and a tool for novices, allowing forward chaining. Okay? This is an example of our activity graph. So stuff that's being added is in black, stuff that's being edited is in gray, stuff below the line are being deleted. Okay? So this is the number of entities being touched, handled, manipulated in a basic unit of time. Okay? So when we look at it, what's the maximum number of things being added in one clear sequence without any pause or break between? 6. What's the maximum number being deleted? Well, we have one instance where they deleted 9 things. They just erased a whole bunch of stuff. Okay? But in terms of adding, they never added more than 6 things at a time. What does that tell you in terms of psychology? How many of you have heard about chunking, information processing in psychology? So, one extreme, you hear the magic 7, that's Newell, and that's that's old school. No one today would argue for the magic number of 7. Okay, fine. You know what they argue for? The magic number of 3 plus or minus maybe 3. So you're talking about 6. So between 3 and 6, 3 and 7 maybe, is what we can handle, manipulate, process in a given single processing activity. We see that here. We're not exceeding that. That's pretty interesting. Okay, so we can't think very far ahead. We can think in terms of 6s. Okay? How does this look a little bit different? So look at this graph versus this graph.
Experience designer.
Yeah. This is the experienced designer. This is the novice designer. Can I quickly tell by their behavior patterns who is experienced and who is novice? I mean, this is a pattern match of 1. All right? So if we find that for 8 more novices, we see a similar pattern, and 8 more experts, we see a similar pattern, then we can start making some conclusions. But just in terms of what they're doing, we don't even have to look at the quality of the solution. Okay? That then raises a very interesting, we can actually monitor how fast people build things and predict whether or not they're going to be good at their job. In fact, a lot of companies do this. When you go for interviews, if they give you a little quiz, they don't care about getting the right answer. They care about how much exploration you do. A lot of times, they'll look at the scratch papers that you're generating and answering those questions, not the actual answers themselves. Because that tells the companies, the HR, more about how you think. This is telling us about how they think. So the novice thinks extremely incrementally. Okay? So we have some challenges. Challenge 1 is study is limited in scope. 2 participants. That's why we have it now with 8 participants. Using the same problem, we could also consider other problems, but in this case, we're just replicating with the same problem. At the end of the day, we want to understand how designers think. So chunking is evident. That is something that no one that I have found in design has found this evidence before. Okay, so we're seeing it. Model growth will vary, we think, based on the level of expertise, which goes back to a lot of the hypotheses that people have developed about experts and novices and how they think through a problem. Experts jump forward. Novices need a much more systematic, step-by-step algorithmic approach. And then finally, designers work with the topology before they work with the vocabulary. Okay? So if they work with the topology and how things connect before they describe what is connecting or what is in the nodes, we can do all kinds of different things. And that, again, goes to reinforce what I talked about last week in terms of using the topology to predict things. Topology is where all the valuable information is, not the actual verbs. And still, we do not know the need for functions in design. Okay? So we haven't answered why should we bother with this. We're just trying to understand the thinking. Okay, that's the next step. Now, the nice thing is that this is enough of an interest that there's a lot of research, and NSF is giving us money to play with this so we can continue the work. We have other open issues, reasoning issues, representation issues, modeling issues, and we're going to focus first on the modeling, tying it with the cognitive psychology. So I'll stop there way over time, sorry about that, but I'll answer any questions that you might have.